Well, I want to say something about twistor theory. Is the sound all right, or is it echoing or something? Turn the sound off. Yes. If I take this out of my pocket, will that cause chaos? It will. So I talk like a natural person, but it still has to. Okay. Okay, that's fine. Right. Yes. Well, I'm going to say something about twistor theory, which is quite a big subject now. So I'll only be able to say something about some of it, and that not in a great deal of detail. I'd like to start by saying something about the motivations from physics, what we were trying to do really, and it's really trying to combine space-time structure with quantum mechanics. It's not really an attempt, at least not at first, an attempt to quantize gravity or something like that. It's trying to bring together aspects of quantum mechanics into space-time structure and vice versa. The view being that ultimately maybe the rules of quantum mechanics will have to shift anyway when combined with those of space-time structure, and so one isn't going to be too rigorous about applying procedures of quantization. Nevertheless, there are many aspects of quantum theory which one likes to sort of bring together with those of space-time structure. I want to mention some things in particular about quantum mechanics. One of them is the fact that it's a non-local. Quantum mechanics is very non-local. Wait a minute. People may be familiar with the things called Einstein-Podolsky-Rosen effects, but there are even more primitive aspects of quantum mechanics which are non-local. In fact, an ordinary wave function of a single particle has a very remarkable sort of non-locality to it, which is very puzzling in a sense. If you imagine a particle here being produced here, and maybe some mirror there, and its wave function will then spread out from the source, and suppose there's a screen down here. Now a wave function is a wave, but it's not like any old wave. That is to say, it's not like a water wave, because a water wave is really a local disturbance. And what the wave does is it tells you the probability of detection, say, at a screen here. Now it has a curious property, as I say, it's not like a water wave, in that detection at one point, say here, forbids the detection of the particle anywhere else. It's just one particle, so when you've detected it, that's it. Whereas if it was a water wave, maybe the wave there would give you some probability of detection here, but the probability of detection here would be completely independent of here. And it doesn't have this curious property that it's like saying detection here, instantly there's a signal goes out to every other place to say you're not allowed to detect the particle. I found it, you see, so there's only one particle. It's a very curious behavior even for a wave, even though you're using the idea of a wave function here. So it has non-local, and it might well be that if you thought in terms of signals, that these 2 points here would be space-like separated. That is to say, these two events would be such that a signal couldn't get from here to here without exceeding the speed of light. So it has that very primitive kind of non-locality. See, the wave function is telling you something about one particle. Detection at one place forbids the detection anywhere else, and if this is an ideal experiment, then it has to be detected somewhere on the screen. And if it was some kind of wave in the ordinary sense, you'd have some superluminal communication involved. So that's one aspect of quantum non-locality, and somehow the idea is that your space-time might have some non-local features if it's to incorporate quantum mechanics in some serious way. Now, something else about quantum mechanics I want to emphasize is that, well, quantum mechanics involves these mysterious linear superpositions. So if you have two states, you can form these combinations with the W and Z being complex numbers. they're treated usually very formally, and the thing you pay attention to is that these complex numbers have connections with probabilities. They're not probabilities because they're complex numbers, but when you make measurements, then these things tell you what the probabilities are. However, there's another aspect to this, is that they have some clear relationship to geometry. And you see this most clearly if you take the quantum mechanical behavior of a particle of spin half. This is, if you like, the most primitive kind of spin. It's the spin of an electron or a proton or a neutron or a quark. And if you have one state, which is the state describing spin right-handed about the upward direction, and this is the orthogonal state right-handed about the downward direction, then every other direction is represented by one of these linear superpositions. And it's a very geometrical thing. Here we have the Riemann sphere of the complex ratio of W over Z over W, and that's U here, and you represent that as a point on the sphere, or we put it on the complex plane going through the equator, and project from the South Pole to some point on the sphere, which now represents U, where the South Pole itself would represent U equals infinity. And this now gives you a point on the sphere. The ratio, we're just talking about the ratio of these two numbers. The ratio is represented by this point on this sphere, and the direction of spin, provided you get your frames organized appropriately, is exactly the direction out from the center of this point. So you see you have this clear relationship between these rather strange and abstract complex amplitudes and geometry. You certainly see it in the case of spin. In other situations, the relation to geometry is still there, but it may sometimes be obscured and not often emphasized by people. But this is a clear case where the relation to geometry is manifest, and you see it's related to this very primitive complex structure, the Riemann sphere, the simplest complex manifold. Now we see a role for the Riemann sphere in a different guise in relativity. It's in fact the celestial sphere. The celestial sphere may be regarded as a Riemann sphere in a different aspect of the Riemann sphere, namely as a conformal sphere. Here you imagine an observer sitting at this event here, looking out at the sky and the various stars. The intersections of the star's world line with the past light cone is what's perceived by this observer, so you draw the light ray from that intersection to the observer's point, and you map the space of these light rays as a sphere. That's the celestial sphere. You imagine out in space and you see the sphere surrounding you, and you might see some stars here. Well, I'm imagining that there are two observers both passing through that same event. So one of them would have one world line going like this, another one at some angle, and they each perceiving the same sky, but you would involve a transformation from one sky to the other, which is the aberration effect, the fact that the stars are like as the Earth goes round in its orbit, the stars slightly shift backwards and forwards. They move forwards in the direction of the Earth in its orbit, and this is an observed effect, but it's a very small effect. If you have very quick motions near the speed of light, then this would be a much bigger effect. But the transformation of the sky is of this particular character, that it's conformal. It sends angles to themselves, and more strikingly, if you like, if you had a pattern of stars which was lying on a circle for one observer, then it would lie on a circle for the other observer. And this suggests that one way of representing this sphere is in terms of complex numbers, and using the complex numbers together with infinity, thinking of this as a Riemann sphere. So we see two roles of the Riemann sphere, one coming from quantum mechanics and the other from relativity, and these also are features of the dimensionality of space. We have to have three space dimensions and one time dimension for this to be the case. Twistor theory is in some ways based on the space-time having three space and one time dimension. And in fact, one can think of it basically as what you're really looking at is the light ray space instead of, you think of the points as the secondary thing and the light rays as the important thing. So this is more or less what we have. This picture is giving us what's going on. Think of Minkowski space, that's flat space-time, pseudo-Euclidean space of 4 dimensions. And we think of the light rays in this space, the straight lines which are tangent to the light cones. And each light ray is represented by a point in some other space. I'm calling this space Pn. The reasons for that will become clearer later. So any light ray is represented by a point, and the light cone of some point in this space, some event here, will be a sphere. That's the sphere of light rays through that point, so we have a sphere over here. And this is naturally thought of as a Riemann sphere. So that's the basic geometry to begin with. The idea is that somehow this space is more basic than that space. You have to think, twistor theory is to say, well, it's not as though you construct that space from this space. You're really thinking of constructing this one from that one. That the twistor space is thought of as more primitive, and you do your physics over here and then translate it over here. You sometimes find things work very beautifully over here, and they're actually simpler than over here. Sometimes it's the other way around. But the sort of driving principle is that in some sense this space here, the twistor space, is more primitive. Now that is just a matter of translation as it stands, but it might have some implications as to what you did later on if you were going to do some kind of quantum gravity theory. And I'll just make the point here. A sort of more conventional way of thinking about quantum, one conventional way of thinking about quantum gravity is you think of the light cones here in your space as being somehow becoming quantum objects. So your metric, this G thing here, would become some kind of quantum operator which you picture as becoming fuzzy in some sense. It's not completely well defined. You'd have some Heisenberg uncertainty and so on and so forth. So you think of the light cone as becoming fuzzy. So that's, if you like, a somewhat conventional attitude to quantum gravity. But the twistor view would be something different, so that your light rays in fact are still there. You know where they are in a sense. I mean, here you don't know what direction. You put it another way, so you don't know which directions are light rays and which directions are something else. Whereas the twistor view is you always know which are the light direction. But what you don't know is when you've got a point or not. So it's the points, if you like, that become fuzzy. And this is more the picture that one is presented with in twistor theory. I won't say that one gets anything like this. It doesn't. Twistor theory doesn't get that far, but that's, if you like, a sort of aim in the distance. The other things I'm mentioning, I will say something more about, such as the non-locality. But let's now say a little bit more about this picture. How do we actually describe this more precisely? Well, what we can do is take ordinary Minkowski coordinates, t, x, y, z. T is the time coordinate and x, y, z are space coordinates. I'm taking the speed of light to be 1 for convenience. And over here, I'm going to use coordinates which are the ratios of 4 complex numbers, z0, z1, z2, and z3, capital Z's. And the relationship between these two pictures is provided by this relationship, which I'm calling the incidence relationship, which is just the first 2 components of the z's here are equal essentially to a matrix of these quantities here times the second 2 components, as written. So you have to combine these in this particular form, z plus or minus t in the diagonal and x plus or minus iy in the anti-diagonal. Now, because there you have 5 dimensions here and 4 dimensions here, the space of light rays is 5-dimensional, and you're looking at ratios of 4 complex numbers, so you're really thinking of 3 complex independent numbers here, so you would have had 6 dimensions on this side so you actually have a condition which has to be satisfied for this correspondence, and in fact that condition is very easy to see, must come about when the coordinates here, when these coordinates are real. This is just showing you how to do it. I won't bother with that too much. I'll be using summation conventions or equivalent quite frequently, so you have to get used to that. Okay, let's just leave that there. Now, one of the driving forces behind twistor theory is that one is really interested in complex geometry. We already see this Riemann sphere here, but the trouble with it, if you like, is that it's sitting in a space which is not a complex manifold, because it's got 5 dimensions, and 5 real dimensions isn't even, and so there's no chance of it being a complex manifold. However, it's not hard to make it one. In fact, you do that by simply relaxing this restriction at the bottom. And what you find, in fact, I'll say a little bit more about this, is that this, if you relax that condition at the bottom, we get now a complex projective space. That's the ratios of the z's without the condition at the bottom there. Just to remind you what that condition is, it's there in the middle, actually. It's that one. If you relax that condition, then we have a complex manifold here, and the Riemann sphere here, in fact, is a complex submanifold of this complex 3-dimensional space. It's a complex line, in fact, in this complex projective free space. And one takes advantage, as we'll see, of the rigidity of complex functions and the notion of cohomology, which comes in, and I'll explain how that works. So this is where we're going to be driven. However, at first sight you say, well, what are these points when the condition is relaxed here, when you don't have that condition there? Well, it turns out that they have a very clear physical interpretation. I've been talking about light rays, but a physical photon actually is more than just a light ray. It has a helicity, so that it actually will spin right-handed or left-handed. Well, some photons are a combination of right and left, but the sort of primitive basic photon, if you like, is either right-handed or left-handed. It spins in one of these 2 directions. And it also has an energy or a frequency, which is another parameter. The amount of the spin is fixed to a definite number, plus or minus 1 in basic units, whereas the energy is another free parameter, or the frequency. And so you now have another dimension, and it turns out that the whole space here, this complex projective space, has an interpretation as these light rays, as the idealized case when the energy becomes infinite, isn't it? I just know. I think which way around it is. Never mind, we'll probably see that in a minute. Okay. That's the sort of physical interpretation of this space here. And so again, you could say, well, we'll do our physics in here, and then interpret things when we want to in space-time terms. Now, it's of some interest that the geometry that we have here is actually some well-known classical geometry. Perhaps I better put all of these together. I hope you can still see what's going on. Can't really see the bottom then, can you? So let's leave that like that. The equations that I've given you here actually correspond to what's known as the Klein correspondence. Goes back to 1870 at least. And this is if we make everything complex. You see the coordinates here, the x, y, z, and t, are normally thought of as real numbers, which is where we get this condition from. But if we make everything complex, this condition at the bottom disappears, and we don't need that now, but and we'll get solutions for the x, y's, and z. If you fix the z's, you can find little x, y's, and z's and t's, and vice versa, and the correspondence you get is exactly the one given here. I wonder if that's the appropriate. Yes. Let me just say that, and I'll come to a bit more of that later on, why that's the case. It is this Klein correspondence. And in fact, a point in the complex projective space corresponds to what's called an alpha plane. I should say that the lines, these are the Riemann spheres, if you like, that I started with, these things here. If you let them roam around now in the complexification of this space, so I'll bring this back again, you let them roam around all over here, then the points, they correspond now to complex points instead of real ones, and you think of this now as complexified Minkowski space. It's actually a quadric, a four-quadric, which would sit in 5 complex dimensions. So you have 5 complex dimensions and 1 quadratic, homogeneous quadratic relation, and if that's satisfied, then you're lying on this complex quadric. CM sharp stands for complex Minkowski space compactified. I'll say a little bit about the compactification shortly, but it's basically Minkowski space complexified, and its points are represented by these Riemann spheres or projective lines in this complex projective 3 space. The points over here, well, before they were light rays, but when you allow this thing to be complex, you get something bigger than that. It's not even just a complexification of a light ray, it's actually a complex 2-plane. And then you have planes here represented by these things called beta planes. The alpha plane is the representative of that. I'll show you how this comes about shortly. And the incidence relation has this, well, the initial one is point lying on a plane here, corresponding to line passing through the point over here, and so on. So this is the geometry that is described here. Just to say something about the compactification of Minkowski space, let me just show you how you can do that. Conformally compactified Minkowski space, that's supposed to be represented by this picture over here. I think that's 4-dimensional Lorentzian space, and I put infinity on it. You can see how this comes about in the following way. Think of a light cone in 6 dimensions, so that this picture down here is supposed to be a cone in 6 dimensions, where I've added to the previous 4 components, t, x, y, and z, 2 more, a w and a v. And one of them occurs in the metric form with a plus sign and one with a minus sign. The metric of this space is meant to be as given here. So I have the standard Minkowski metric in the middle here with an additional plus term for the w and a minus term for the v. So this is a signature 2,4. And if you now take the section by w minus v equals 1, this so here we have w minus v equals 0 is that one, and if you move it along, that's w minus v equals 1. That chops the cone in this paraboloidal thing. Of course, the dimensions in this picture are too small. You have to think of this cone here as being, the whole space is 6-dimensional, this cone is 5-dimensional, the plane here is another 4-dimensional, is a 3-dimensional plane. Sorry, the whole plane is 6-dimensional, so that's a 5-dimensional plane, and the intersection of these two 5-dimensional things is a 4-dimensional thing. So this red thing that looks like a parabola is really a 4-dimensional space, which is given by fixing w minus v equals 1. So you've got t, x, y, and z to coordinatize this thing, and the metric on it is just going to be the ordinary Minkowski metric, because these two things kill each other off, and you just have that term. So you see this is Minkowski space sitting in this slightly strange way in this six-dimensional space. Now I'm going to consider the rays through the origin here, and most of these rays will hit the Minkowski space, so the space of rays through the origin is Minkowski space, except in addition we're going to have those rays which are in the plane W minus V equals 0, parallel to this plane here, and those are out at infinity on the Minkowski space. So you've incorporated infinity as well, and you can see it's a compact space because it's simply the space of these rays through the origin here. So it's a quadric, in fact, in projective 5 space, which is exactly this object here. So that's what we've got, except it's real here. But you can imagine these coordinates becoming complex, and then it would be this space here. And this is Minkowski space, together with the bit that you get lying in this plane W minus V equals 0, and that's what we think of as the light cone at infinity. So you've taken Minkowski space and you've added this light cone at infinity, and the whole thing becomes compact because the path that, well, once you go up here, that's sort of identified with down here. I won't say too much more about that, except to say how it relates to this picture down here. The light cone at infinity is a particular cone on that space there. It's given by the equation z2 equals z3 equals 0. It's a section of this quadric by a plane, appropriate. What is it? It's appropriate dimension. And there we have this particular line representing this light cone at infinity. So there's a particular line which we call I sometimes, representing infinity, but everything else is a finite. Every finite thing here is represented by a point away from that line. Actually, lines which meet this line are points on the light cone at infinity. Lines which are skew to this line are the finite points in the Minkowski space. Okay, so that's the geometry. And we see this goes back to Klein, if you like, in 1870. Well, in a certain sense, it goes back further than that, because Felicity in 1869 apparently noticed that if you take oriented spheres in E3, well, I think it must be complexified E3, otherwise it doesn't quite work. So let's say it's complex Euclidean 3 space, and these spheres are meant to be oriented. And what he noted was that you can represent those by lines in a complex projective 3 space. Now, what's that got to do with the twistor correspondence? Well, first of all, I should say that contact, these are oriented, so you think of an arrow pointing out or in, and contact between these spheres is to be only considered when the orientations are consistent. So the arrows have to agree with each other, and you have 2 places where they do agree, there and there, and that corresponds to lines which actually intersect in this correspondence. And that has to do with Minkowski space, because you think of space-time here, and you take a single moment of time and slice through it, space-like slice through it, and that intersects the various light cones in these spheres. So that sphere is represented by this light cone here, and that really represents this point in Minkowski space. If it's oriented one way, it's above the plane. If it's oriented the other way, it's below the plane. And if you have contact, as here, consistently, then that means these 2 points have a line, a null line, joining them. In this case, you have that too. So this correspondence there is basically the one I've been telling you, but it was pointed out by Felicity in 1869. But as far as I'm aware, none of these people had the view that one should do physics in this space. So that's really what twistor theory is about. Okay, well, let's carry this on now and go back to this particular relationship that we had, which was the incidence relationship. And I'm going to write it, well, this is where people tend to get a bit confused because of the notation. But it's a very handy notation. So this is the incidence relation, which we just had, and I'm going to write it as this expression underneath. Omega stands for these two components, and pi stands for these two components. And they've got a capital index. This is a two-dimensional index, so you can think of that as taking the values 0 and 1. And this is a primed index, which also takes the values 0 prime and 1 prime, which are 2 and 3 in the opposite position, if you like. And there is this correspondence between this combination of coordinates, Minkowski coordinates, and this 2 by 2 matrix here, and that's conveniently written this way. This is the two-spinner notation, which I'm not assuming people are familiar with, but it's very handy. So I'm afraid I will use this notation quite often. It's extremely handy, but it takes a little while to get used to it. Roughly speaking, you have these capital alphabets to represent the spinor indices. They're two-dimensional. If you think in terms of components, they take the values 0 and 1, and these ones 0 prime and 1 prime, where the tensor indices take the values 0, 1, 2, and 3. I prefer to think of these things really as abstract, so they're the letters refer to an abstract object. So this is, you can think of it as components if you like, but it's handier if you actually don't think of them as components, because it means you can do things like this. You see, A is really a combination of the capital. The little a is a combination of the capital one primed and one unprimed, and so on. So it's a tensor product of the space of these two things here. Well, don't worry too much about that, but it's handy because you can, the metric has this behavior of splitting into two skew symmetrical things. I'll just leave the notation there, so if you I won't say too much about the details of this, but it is a very handy notation. Anyway, the two components, the Z0 and Z1, correspond to this thing omega, and these other two components to this thing pi. Now, omega and pi have somewhat different physical interpretations. The pi, the reason for the letter pi, in fact, is that it corresponds to momentum. We see this at the bottom here. Let me say this first, and then I'll come back to this. If you have a massless particle, remember I had these things looking like little corkscrews in the picture here, whichever it was. Where did I put it now? Here it is. I better put the notation back again in a minute, but remember the objects here, which represent massless particles, well, I call them photons. Think of them as describing massless particles, and they can be spinning right-handed or left-handed, but they have an angular momentum as well as a momentum. And the momentum is described by this thing P. They're null, that is to say they point along the light cone, so that they have 0 Minkowskian length. There they are, with P0 positive, which means that they point along the future light cone and not the past light cone. The M thing is a two-index object. It's basically a two-form, if you like, skew symmetrical, which has 6 independent components, which encompasses the relativistic angular momentum. Angular momentum in relativity has 6 components, corresponding to ordinary angular momentum and the motion of the mass center. That's the 3 other components you get. There's a thing called the Pauli-Lubansky spin vector, which is given by this expression using index notation, or it's the dual of P wedge M, if you prefer a notation without any indices. And this Pauli-Lubansky spin vector has the virtue that it's independent of the origin. Let me go back up here now. So if you move the origin from a place, if you start with the origin at O and you move it to a point Q, then your original r, which appears in this expression, becomes r minus q, and your incidence relation now goes over to, well, if the pi's are considered to be independent of the origin, they're momentum things, so they don't depend on any origin, but the omegas are more like angular momentum things, and they will shift as the origin is moved. So you have this relation here. With respect to q, there is this relation to the ones where with respect to O. So that's the shifting of origin is given by that. And if you use the formula which I've got at the bottom here, see what you find is that if you're given an omega and a pi, then you plug them in this formula at the bottom, and you get a momentum and an angular momentum. And this momentum and angular momentum automatically satisfy the relations, well, that P is null, future pointing. The Pauli-Lubansky thing here, and I didn't say this before, but the Pauli-Lubansky vector for a massless particle should be proportional to the momentum. This is a condition which ordinary particles are supposed to satisfy, massless particles are supposed to satisfy. So you have, this is proportional to that, and the ratio, the proportionality factor, is a thing called the helicity. So this helicity tells you which way it's spinning. If it's positive, it's right-handed. If it's negative, it's left-handed. And it's an important quantity defined by a massless particle. And this is, you notice it's a sort of non-linear relation having to be satisfied by P and M. So the conventional way of describing a massless particle would be to use P and M, and it's quite complicated, you see. You've got these complicated relationships, whereas the twister does it automatically for you in a very simple way. These things now become independent quantities. Under change of origin, you see the M's also change in a complicated way. This Pauli thing doesn't change under change of origin, but the omega changes in a much simpler way than the angular momentum does. It's a very simple expression here. And you find that these relations are all satisfied automatically by this expression here. Let me just say something about the expression. The P here is the product of the pi with its complex conjugate, and this is a particular instance of this general property here. If you want to interpret a spin vector, a spinner with a single index here, you multiply by its complex conjugate, and it determines a null vector for you. It also has a phase, which determines a direction along the light cone. There's a little plane element which is tangent to the light cone. Don't worry about the details of that, but it just, if you want to describe null objects, null vectors, in this two-component spinner notation is very convenient. So the P is naturally in terms of the pi, and the M is now given by this slightly more complicated expression, where these round brackets mean symmetrization. It's omega symmetric product with the complex conjugate of pi, and this epsilon is a symmetrical object which plays the role of a metric in the spin space. It's really a symplectic structure, if you like, antisymmetrical, and two of them together give you the metric. That's how it works. Don't worry too much about the exact expressions. I'm afraid I'm going to have to throw them at you rather, but that is the way one goes from the two parts of a twister to the momentum and angular momentum. It's an explicit formula here. The only time when this doesn't quite work, if you like, is when pi equals 0. If pi equals 0, then m is 0 and p equals 0, so you don't have any physical interpretation. It's sort of a limiting case of a particle of zero momentum, but it still has a spin. So the spin, sort of disembodied spin hanging around. But never mind about that limit. Okay, so that's the physical interpretation of a twister. I think I should probably give you this. I'd more or less said this before, but it just tells you what the alpha plane is, if you like. if you're just looking at real Minkowski, if this R is a real vector, then the points which are incident your twistor, I mean the real points which are incident with the twistor, if there are any at all, will be on the light ray. But if R is complex, then the points which are incident with the twistor give this thing the alpha plane, and that was the alpha plane which I referred to in the Klein correspondence. Okay, so that's that. So that's just basic geometry. I suppose it's worth saying this thing here. Twistor theory, which I regard as physical twistor theory, if you like, is one where the space-time has this signature with Lorentzian signature. And then you find that the complex conjugate of a twistor is a dual twistor. This is, I don't think I stressed that before, but the complex conjugate of a twistor is a dual twistor. I think that appeared in my expression here. It is just here, you see. The complex conjugate of a twistor, the index goes downstairs, so that makes it dual. And when you look at these two parts to the twistor, the complex conjugate of a pi loses its prime, and the complex conjugate of omega gains a prime. But you put them in the opposite location, and then you see this is dual to that one, and that's dual to this one. So that when you multiply z by z bar, you take this times this plus this times this. And that's the scalar product between a twistor and a dual twistor. Now this is a feature of the physical Lorentzian signature. Some people use twistor theory in a different context, where you have a all positive definite, and then the complex conjugate relation sends a twistor to a twistor, not a dual twistor. And the flavor of the subject is somewhat different. The other case that people sometimes consider is the split signature Minkowski space, and then the complex conjugation is also sends a twistor to a twistor. In this case, you actually have real twistors. There are solutions of this equals this. In this case, there are no solutions of this equals this. But you see the different character that one has for different space-time signatures. And in pure mathematics, the applications of twistor theory tend to be sort of like this, or sometimes this, with some recent work of Witten in twistor theory. He tends to use this signature here. But this is the directly physical one, is this one here, and that's what I'm using. Okay, I guess I probably, yeah, we didn't start till a little bit late, so perhaps I could make these comments too. If you have points in complex Minkowski space, they're really of 6 different kinds, depending on what happens to the imaginary part. See, if you have a point in Minkowski space, the imaginary part, well, it'll have either it's time-like, that's within the future cone, or future time-like, or past time-like, or it could be future null, or past null, or it could be space-like, or it could be 0. 0, that's a real point. And the twistor representation of this complex point, depending on these different possibilities, color-coded over here. So I think, let me specifically say the ones where you have a imaginary part to your complex position vector, which is past pointing, and that corresponds to a line in the future half of twistor space. And that's important because this region here, that is to say the complex points with past pointing imaginary part, what are called the forward tube of complex Minkowski space. And this has a significance in quantum field theory. You want your wave functions to extend into this forward tube, and that ensures that they have what's called positive frequency. And a wave function is supposed to have positive frequency if it's a free particle. And the thing is, twistor theory copes with that by saying you're talking about the top half of twistor space, because that's where the vector is, the imaginary part is pointing into the past. That will have a role to play in something I will say shortly. Okay. What I want to do next, however, is to consider what might be called quantum twistor theory. quantum twistor theory, we allow these z's and z bars to become non-commuting objects. It's like what you do in standard physics, where you take momentum and position and momentum become non-commuting objects. And that's what you're doing here. But now it's the twistor and its complex conjugate become canonically conjugate objects, so that the z's commute with themselves, the z bars commute with themselves, but the z's and the z bars have this commutation relation. Now this looks like sort of taken out of the hat, but that's what you do in quantum mechanics. You more or less do take something out of the hat like that. Now this was our real, our classical non-quantum twistor theory, and we had this expression relating the twistors to the angular momentum of a massless particle, where you now do the same thing, but where these z's are now considered to be quantum operators. And that means that the omegas and the pi's are now quantum operators, and by virtue of these commutation relations here, they also have certain commutation relations. The pi's commute with themselves, and they commute with the pi bars. The omegas commute with themselves and with the omega bars, but the pi's and the omegas, or the pi's and the omega bars, have a commutation rule. The momentum and angular momentum expressions are exactly the same as before. There is no problem about factor ordering, because these things commute. These things don't commute, but the commutator of omega and pi is this spinor epsilon, which is killed off by the symmetry bracket. So you don't have any problem with that. So these expressions are undisturbed by factor ordering, but the quantity S, which is the helicity, is actually slightly changed, in that you just go through the algebra here and see what S is, bearing in mind that things don't commute now, and you find that the S is the polarized form of this, so it's not just z bar, but it's z bar plus z bar z divided by 4. I tend to take h bar equals 1. You may find on some of my slides it's gone back to being not equal to 1, but that's just because I make these slides at different times, and I may forget what conventions I've adopted previously, but you can always put it equal to 1 quite safely. There are standard commutators between the momentum and angular momentum, which are these somewhat complicated expressions. These, in fact, give you the Lie algebra of the Poincaré group, that is the Euclidean group in the Lorentzian signature. That is now something which is automatic from the twistor relations. It's rather elegant. You see, the twistor commutators are these very simple basic expressions, and you get these rather complicated looking expressions for the standard commutators simply by plugging the twistor commutators into this expression here. Okay. Now, what's a twistor wave function? We're supposed to be describing a massless particle. What's a twistor wave function? Well, you see, z and z bar are conjugate variables, and the twistor wave function ought to depend either on z or on z bar, but not both. See, this is the same thing you do in ordinary quantum mechanics. If you have position and momentum, then your wave function, either you think of it as a function of position, that when you say wave function you usually mean a function of position, but there's no momentum in the expression. The momentum is now d by d position, and then you get the commutators right. You do the same thing here. Well, also in standard physics you can take the momentum instead, if you like, and then position doesn't appear in your wave function, but position now is d by d momentum. So that's the rule you adopt here. A wave function should be just a function of one, but not the other. Well, what does that mean? Say it's a function of z and not of z bar. Well, that means the partial derivative of f with respect to z bar is naught, and these are just the Cauchy-Riemann equations. So this asserts that f is holomorphic, complex analytic. So f is a complex analytic function of z. So you're automatically driven to thinking about holomorphic functions from these commutation rules. Now, what about helicity eigenstate. Suppose you want to say that your massless particle has a definite value for its helicity. That means it's an eigenstate of the helicity operator. Now this is an operator now, and you simply look at the expression that we had before, this thing here, and see what that operator is, or what the eigenstates of that operator are. And well, z bar is just basically minus z d by dz, and that is the Euler homogeneity operator, whose eigenstates are homogeneous functions. So that's the Euler homogeneity operator, and so therefore the eigenstates of S are homogeneous functions, and so you're talking now about holomorphic homogeneous functions to describe particles of definite helicity. If the helicity, well, if n is twice the helicity, now I've brought h bar back, but forget it. N is twice the helicity, then the homogeneous degree would be minus 2 minus n. Now what does that mean? I mean, I've just formally written that down, and you might ask, what on earth does all that mean? Well, we need to see what the massless field equations are. If you have in ordinary formalism, if you want to write down the equation for a particle which is massless and which has a definite helicity, well, the equations are, I'm afraid this uses this two-spinner notation, but there it is. It's very simple, actually. You have an object with, if you have a negative helicity of minus n over 2, then you have an object with n indices which is completely symmetrical, satisfying this basic field equation. This is the wave equation if helicity is 0, and it's the same equation but with prime indices, same equation as this, but with prime indices if the helicity is plus n over 2. In fact, those equations, although they may not look familiar, really do encompass the standard things like Maxwell equations. Maxwell equations, you write in terms of a 2 form. Well, I've written it with indices here, so this is basically a 2 form. And these are the Maxwell equations. This says d of f equals naught. This has these, well, here I've written it, d of f equals naught, or d star of f equals naught. And those are the free Maxwell equations. But if you write it in spinors, then it's this expression. So you have the left-handed part and the right-handed part. These are the eigenstates of spin minus 1 and spin plus 1. And you find these equations here. These are just the particular case of these equations over here where you have 2 indices. So this gives you the 2 helicities for the Maxwell field, and exactly the equations written up there in this particular case. But you also get the things like the linearized Einstein equations. See, if you're working with curved space-time, you'd have a curvature which for vacuum, Einstein vacuum, your curvature would satisfy the equations I've got written down here. This is the Bianchi identity, and its vanishing trace, that's the Ricci tensor vanishes, and so on. And this is the Bianchi symmetry. These are the equations that you would get for the curvature in vacuum, as I say, Ricci flatness, and then the linearized equations mean you take the limit as the space goes to flat space, and these represent the first order deviation from flatness. But they're linear thing. It's a linear equation. It's the weak field limit of the Einstein equations. And again, you can write these k's in terms of these psi and phi. Now 4 spinor indices, and these are exactly the same equations, but now with 4 indices. So you see that the linearized Einstein equations are also encompassed in this scheme. The neutrino equations for a massless neutrino are encompassed as well. In fact, I've got them all written down here. The scalar wave equation is part of it. That's that one. These are the Dirac-Weil equations for massless neutrino or antineutrino. And here we have the Maxwell equations. And These are the self-dual and anti-self-dual parts, or the left and right-handed parts, and the linearized Einstein equations also. Okay, now these would therefore correspond in this twistor description to, these are the spins here, they would correspond to these homogeneities. This is exactly the formula that I just gave you, the helicity in terms of the, well, I guess it's down here, is it? No, it isn't. It's that expression there. But, so we have now a twistor description, which is just a homogeneous holomorphic function with this homogeneity degree, and in space-time we've got these funny-looking equations when the spinor form. How do we get from one to the other? Well, the answer is as follows. Here we have the twistor expression, and what we're going to do is a contour integral on that. You see, this depends on omega and pi, and what I say, let's just integrate over the region where x is incident with the twistor omega pi. That's the incidence relation, if you remember. And we integrate out the pi dependence. And so we end up with something which is a function of x. And if this is just this expression, then you get a solution of the wave equation. In fact, it's a general solution of the wave equation. There are two ways of doing this, either in one dimension or two dimensions. I'll say a little bit about that later on. For the pictures, let's assume it's the one-dimensional version, which is this one here. If we're looking at, this is the case where f has homogeneity minus 2, so the homogeneity is balanced. This has homogeneity 2, that's minus 2, and when you integrate it out, that's all you need to do. In the case where this thing's got some indices, the f has homogeneity, well, less than minus 2 in this case, and so you put some pi's in there to balance the homogeneity, so the total homogeneity is n, or whatever it is there, and 2 from here, and that gives you right number of indices over here. And if it's the negative helicity case, where this thing is greater than minus 2, you differentiate a few times with respect to omega, and that balances it now, and so you have the psi thing. And what you find is that because of these expressions, these field equations are automatically satisfied. So the equations that we had at the top are automatic consequences of the contour integral expression. In fact, if you go back, I've mentioned a few things which were the geometry which were known way back, in fact, in the 19th century. In fact, versions of this formula which I've given you, not quite written as contour integrals, but written in a way equivalent to that, were obtained by Whittaker in 1903. This is actually just the scalar version here. So Whittaker, I'm not sure if he found the full four-dimensional version, and that may have been Bateman, but that's only 1904, so it wasn't much later. So Bateman certainly had the formula for the Felicity zero case, but he also, in 1944 at least, I think a little earlier, wrote down the formula for the Maxwell case. Let's see, which one was it? It's basically this case with F homogeneity minus 2. He didn't write it that way at all, but it was essentially this formula here in that case. But this shows that these actually generalize to completely general expressions, and we can understand a bit more about what's going on. Let me just give you some examples. This is the sort of most basic example in the case of helicity 0, where the function f has homogeneity minus 2, and the simplest expression you can write down is 1 over the product of two linear factors. These are homogeneous linear factors. The vanishing is on a plane in twistor space, so here we have projective twistor space. The green one represents A, and the orange one represents B. Those are two planes. And the contour integral, well, you see, we need the point x to come into it. X is represented by a line in twistor space. I've written this as a rather long sausage if you think it's really a Riemann sphere. So that line is this Riemann sphere. It intersects these two planes. This is where the poles occur in this expression, in 2 points. Those 2 points are the green one and the orange one here. and the contour integral runs around between the two and gives you a finite answer, and the solution to that answer, this gives you the field. It's the solution to the wave equation. This is using this version for the delta pi, where you really are doing a one-dimensional contour. There are advantages in the two-dimensional case, which I'll say shortly, but let's not worry about that for the moment. You can generalize this idea to functions which aren't just poles. They can have big regions of singularity, and I've now indicated this by sort of two camel humps here. This is the singularity of your holomorphic function in twistor space, and I'm supposing that the camel humps are two separated regions, two closed sets which are disjoint, and that if I take the line in the top half of twistor space here to intersect these two humps, there will always be some region that I can do my contour integration here. If you remember, the virtue of this top half region is that that corresponds to the forward tube, and this means that the functions you get this way extend automatically into the forward tube, and therefore they are automatically positive frequency, which is this requirement for a wave function. So you actually do all sorts of things at once with this expression. You have something which is the right helicity, satisfies the field equations, and is automatically positive frequency if your humps are separated in the top half. And that's just what you want for a wave function. Now, there's still something a little odd about this expression, because I've just put another picture down here because I couldn't make up my mind which ones to use for this talk, but it's basically saying the same thing. This is a somewhat confusing expression, because you might imagine, after all, the solutions of the equation form a linear space, and you can add two of them. You might imagine adding these various functions with their singularities together, and if you add too many of them together, especially if you've got spread out regions for their singularities, they'll start overlapping, and you might have nowhere to put your contour, and so you wouldn't know what to do. So it needs a deeper understanding of what's going on, and this can be obtained if we proceed as follows. What I'm going to think of, you see, it's a little bit awkward to think of this top half of twistor space with the two camel humps removed. So let's think of it rather differently. I'm going to think of the top half of twistor space as the union of two regions where each of them has one camel hump removed, and the intersection of these two regions is the one where the function is defined with two camel humps removed. So this is the domain of definition of our function f, and this is the region we're interested in. So notice the region we're interested in is the union of these two regions, and the domain of definition of the function is the intersection of these two regions. Well, this is actually telling us what we're really doing is check sheaf cohomology. You see, in this case, u1 and u2 would be two regions. The function, the holomorphic function we're concerned with, is defined on the intersection of those two regions, and the union of the two regions is what we're interested in. More generally, you might have a whole lot of sets covering the region of interest. This is the PT plus, could be covered by a whole lot of open sets, and we could have a lot of f's on their various intersections, on their overlaps, and you need to have a condition on triple overlaps, and you need to have a condition that if that the function is equivalent to one where you can add or subtract regions defined on just one of these regions independently. Well, this is just the definition of a check cocycle. So what we say is that our twistor function, if you had a covering with lots and lots of open sets, your twistor function would consist of a lot of f's, skew symmetrical, so that if you interchange the u's, the f's are supposed to go to their negatives, and this collection of f's is a check cocycle. And then, given the check cocycle, you can define a generalized kind of contour integral where you have a branch contour like this, and so on. I'll say a little bit more about this, which is why one of the reasons it's important. Oh dear, yes, I see I've... what will I do about the time? Well, I'll say a few more things and then I'll stop, I think. There are so many more things to say I could just go on all afternoon, which I think I won't do, and since there's tea waiting for us. Let me just say something, though, about a couple of things about the importance of this being check cohomology. Sometimes people worry, you see, physicists, if they don't know anything about this check cohomology, they sort of turn off at this point, if they haven't turned off a lot earlier. But there actually, it's a very important aspect of twistor theory. One of them I only just realized about a year ago, which is a very striking fact. First of all, let me give you a rather primitive notion of cohomology here. This impossible triangle is actually an illustration of cohomology. The cohomology is a precise non-local measure of the degree of impossibility of that picture. And how do we understand that? Well, you see, I'm going to talk about check cohomology. And here, you see, that means that first of all, I split this thing up into its open sets. There they are. And each of those represents a perfectly possible object. But I patch them, you see, according to, I say, my patching function tells you how far away this is relative to this and so on. And if the cohomology element vanishes, then it's a possible object. So I rather like that. It's a way of saying what cohomology is to people who don't know anything about it. So, but let me say something else. This is something I only realized fairly recently. I started off my lecture with this here. Now you see, one of the things that often worried me is that twistor theory is supposed to be a non-local description of things, and I'd always had in mind these Einstein-Podolsky-Rosen things where you have particles in opposite corners of the room and they seem to be not independent of each other in some sense. What I hadn't thought of is the more primitive type of non-locality, which I described here, which single wave functions have. You see, the twistor description is of a single wave function primitive. I just thought, you see, in describing fields or something like that, but they're really, basically, we're talking about single wave functions. So this thing here, in its twistor description, is a cohomology element. And when you measure it here, that means you're, roughly speaking, saying, well, take your picture and you tap off part of it and join it onto some other structure, you see. But that's breaking this thing here, and once that's gone, the tension in that object has disappeared. So that the measurement of the particle, the photon here, has relieved the tension in the object. The cohomology is now gone, and there's nowhere else to find it. So it has automatically the non-local character that one sees here. So I regard this as actually a really positive aspect of the fact that one is twistor wave functions are cohomological objects, and this gives them just the kind of non-locality that one requires for this physical phenomenon over here. Let me move to one other thing, and then perhaps, or two other things, yes. I'll just say this bit. I almost said this already, but there was a sort of early motivation of twistor theory, which took a long time to be realized, which was somehow that this positive-negative frequency splitting something that you easily get on the Riemann sphere. If you have a function defined on this equator, then the positive frequency ones extend into the, well, let's say, northern hemisphere, and the negative ones into the southern hemisphere. And twistor theory exactly does this, but not now for functions. These are functions, but it does this for first cohomology. And that's exactly what one wants if first cohomology is describing wave functions. Okay, so that's one point. Another point is that it allows for nonlinear generalizations. You can think of the cohomology element as something painted on your space, roughly speaking. But if you now think of what's on the space is, say, a vector field, which represents a kind of deformation that you can make. So you slide these patches according to the vector fields. and you have a consistency condition on triple overlaps and so on. Well, this corresponds to building a manifold. That's really what you're doing, or deforming a manifold, if you like. And this is a kind of non-linearization of the cohomology. And what this does for you, and I'll just flash this picture up, but it actually very explicitly does for you. I mentioned linear Einstein theory, but it actually gives you a nonlinear description where the full complex Riemannian geometry is described. You have Ricci flatness as a consequence. I don't think I can go into that, especially since there's no time left, but I think I'll end by giving you, see, a nonlinear element is where you actually deform the space by shifting these things over each other. And there are various versions of that in constructions of anti-self dual spaces and so on. One big problem that's been with us for a long time is what we call the Googly Problem, and that is that we have a very nice way of doing, and that's here, the left-handed graviton, if you like, gives you a nonlinear deformation of a function. See, this is originally a function homogeneous with degree plus 2, and you can use that to generate a finite deformation, and that gives you a solution of the Einstein equations, which is anti-self-dual. That means it's negative helicity. It's a negative helicity graviton, if you like. But then how do you do the positive helicity graviton? And that is still not fully understood, although I think there's some genuine progress has been made. Why is it called the Googly? Well, Americans probably wouldn't know this, but people who come from India or Australia or something be more familiar, because it's a cricketing term. So it's a cricket ball bowled so as to look as though it spins left-handed, whereas actually it spins right-handed. And that's what the googly thing is. How do you solve the problem? You see, the plus homogeneity 2 functions very naturally give you the solution of the Einstein equations with negative helicity, but the ones with positive helicity are much more obscure. I think it's possibly that this is the right answer here, but to see how to make it work is quite tricky. I think I'll end with just a comment about recent things, where Ed Witten wrote a paper towards the end of 2003 in which he tried to use string ideas to in twistor space rather than in space-time. See, we have a complex manifold, which is this projective twistor space, just sitting there waiting for strings to be put in it, whereas what string theorists normally do is they add a lot of extra space dimensions onto space-time and put the strings in those extra dimensions, basically make them into complex manifolds and so on, which are natural places for complex curves to sit. But twistor space is in a certain sense already a natural place for complex curves to sit. Now, the situation is more complicated than I just said, but in a certain sense it is a very natural place to think of strings, and there has been a very interesting development of how to make string theory give new insights, first of all into twistor theory, and secondly into explicit calculations for scattering processes which can be measured in accelerators. So you're looking at what are called gluon scatterings or Yang-Mills interactions, and these things are important actually in observational physics, and the very, very complicated calculations that have been done in conventional ways have been shown to be vastly simplifiable using these twistor string procedures. Very recently, my colleague Andrew Hodges, who has been, I would say, the world expert on twistor diagram theory. Twistor diagrams are the analogues of Feynman diagrams for twistor theory, and he has been very much stimulated by this work in twistor string theory, and work that he had been doing years and years ago has sort of got revived and moved onwards. So he is now, I think, gone ahead of the twistor string people who can actually show how to calculate very complicated processes directly using the procedures of twistor diagrams. So I just want to say that there is a very active end on the physics side of twistor theory. There's a lot of use of twistor theory in pure mathematics, which I haven't really referred to here. Differential geometry, representation theory, and integrable systems have all benefited from insights coming from twistor theory. But as a physical theory, the Googly Problem has been one of the big hold-ups in the subject. I wouldn't say that we still got over it completely, but there are ideas which at least seem to be moving forward here. But more immediately, we have these ideas of twistor diagrams, which do seem to give calculations which certainly haven't been doable before. They've just been far too complicated, whereas twistor theory shows how you can do these things in very simple terms once you've understood the twistor theory. It takes a little time to understand the twistor theory, and I imagine it'll be a while before these things become common usage. Anyway, I better leave you with that. Thank you very much.